Okay, so based on the information about HIN we defined before, then we can further consider how can we embedding this HIN into some concise embedding vectors with graph neural networks. We know that for the conventional homogeneous graphs with one single type of nodes and one single type of edges, then we can apply the conventional GCM model for learning the representations of nodes inside graphs, right? And when it comes to the heterogeneous information networks, then how can we learn the embedding vectors of the nodes inside graphs? Do we need to do any extensions of the conventional graph neural networks to handle the different categories of nodes and the connection among them or not? So before we talk about the extensions, we can discuss about the conventional GCM model first, and we can do a revisit for the operator we define inside this GCM model. So we know that for the HIN, we have different categories of nodes and different categories of links among them, right? So here we can start the graph with one single category of nodes and one single category of links, which will be the GCM model we discussed before, right? So for the conventional GCM model, I hope you still remember how do we define the representation learning for the nodes inside graph structures. If you still remember, in the GCM model, we have an operator which is called SGC operator, the spatial graph convolution operator, right? We can define for learning the representation of the nodes by aggregating information from the nearby nodes or neighborhood nodes, for defining the embedding vectors. As shown in this page, given an input graph like this one, right? We have, if we consider the A as one of the target node we are starting here, then we can learn the embedding vectors for the A as HA as shown here, right? So we can learn the HA, the embedding vector of A node by a NN model or NN component as shown here, right? This NN we aggregate information from the nearby neighbors, to learn the representation for the A node. So they receive input from the B, C, D, E, F as the inputs, their nearby neighbors connected to A node. So by aggregating all the information from the HB and THF as the inputs, we try to integrate all the information from the neighbors, to learn the representation for A node, with this NN component, right? For this HB, HC, and so forth, they will also aggregate information from the neighbor, representations of the nearby, their own nearby and neighborhood instead, right, and so forth. So as to how to define this NN component, I hope you still remember the formula we use for defining this NN component. So we can represent the formula for updating the node representation like HA for the case layer. It equals to the sigma function is the activation function. Inside it, we do the aggregation for all the nearby neighbors of the A, right? It's gamma A denoting the neighborhood set of the A node. And we enumerate all the nodes, all the neighborhood nodes of A inside the graph structure, and we try to aggregate their representations together for defining the A's representation, right? And we also assign the representation from different neighbors with a scalar. This scalar denotes the importance of different neighborhood nodes, right? And the scalar is defined by the reverse of the degree for the neighborhood nodes, like gamma V 1 over gamma V, as shown here. It's gamma V denoting the neighborhood of the V node, right? It denotes the degree for V node inside the graph structure. So by aggregating all the neighborhood nodes together, then we can further time this one with one variable, like W1 as shown here, right? And we also sum this representation by aggregating all from the neighborhood together with the lower neighbor representation of the A itself from the lower neighbor of the model, right? Like K-1 layer. And the way we can be denoted by the W2, this matrix as shown here. And then this W1, W2 is the other variable to be learned inside the model, right? This is for the conventional, GCM model for the homogeneous graphs with one single kind of node and one single type of edges, right? And when it comes to the heterogeneous information network with different category of nodes and different category of edges, then how can we deal with them? Here, if we assume this A as a target node, we know that connecting the A, we have different category of edges or relationships, right? Now R1 and R2 as shown here. This B and D, they are connected to A via this R1, this category of edges, and this C will be connected to A via this R2, this edge, this category of edges, right? This is R1, R2 denoting the category of links, connecting the nodes. Besides R1 and R2, we also have some other category of edges like R3 and so forth inside the graph as well, because we are studying the heterogeneous information networks. Of course, these nodes will also belong to different categories. So therefore, when we consider to do the aggregation, from the nearby neighborhood, we will need to further consider the category of nodes as well as the category of edges that we define here. So we know that different category of edges, they can carry different kinds of physical meanings. Therefore, to differentiate them from each other, we prefer to define different variables, doublet metrics for each category of edges inside the graph structure. Now, for R1, this type of relationship among the nodes, we can define a unique variable WR1 for its category of links. If we have any links belong to this category, then we can denote the corresponding variables for the type of edges as WR1, for example. In a similar way, we can also define WR2 for the relationship R2 and so forth for other relationship categories. So based on this intuition, we can redefine the formula we write here for the conventional GCM model into a new way by considering the type of edges connecting the nodes inside the graph structure, inside its HRN graph structure. So by considering the relationship of these categories, we can rewrite this formula we defined above into this one instead. We are still trying to update this A's representation as a target node with the operator. However, we do some updating for the formula we defined before. We are still doing the aggregation. However, for the aggregation from the nearby neighborhood, we prefer to further consider the types of edges connecting them. And we can denote this R, the category R denoting the set of different category of relationships we have. And for each category of relationship inside R set, and we can define one unique relationship variable like WR for the case A as shown here. And if we further consider the relationship connecting nodes, then we can partition the neighbors of node A into different subsets by considering the relationship types. And we can define a notation gamma A R. This is one denoting the set of neighbors which are connected to A and Y the relationship R. Now, for example, if we consider A is a user node and we consider this R denoting the friendship among users, then this V, will be all the nodes who are connected to the node user A via the friendship links. On the other hand, if we consider R to be the location checking a relationship and this type of relation, then we can further define gamma AR representing the set of location check-ins, which the user A has ever checked in the offline world instead, right? Then this gamma AR will cover all the location check-ins instead. So by considering the connection types, we can categorize the neighbors of node A into different subsets, right? So for the neighbors belong to each of the categories, connecting to A, then we can further aggregate them, representation together, by a similar formula as shown here, right? We aggregate the representations from the node level, case -1's layer, and we also have a scalar denoting the importance of this term, right? Which is 1 over gamma AR, because here we could consider these link types as we show here, right? So by aggregating these kinds of different category relationships, among connecting to the user A, we can first, integrate of the user A to shift, which is parameterized by W1 as a variable to be learned. So you can see by considering the link types, we can define more variables to differentiate each kind of relationship from each other. Right? Then in this way, we can ensure this model can capture the physical meanings of different relationships among the nodes. That's the reason why this model is called the relational GCM model, or RGCM model for short. It can consider the relation types inside HRN, these networks. So here we provide you with more detailed information for this formula. So for each edge type or for each link type R, we can get the neighborhood of A as gamma AR, right? And we also define one unique weight variable matrix for the relation R, which will be the WRK for each layer of the model. And we aggregate information from neighbors in this gamma AR, by the term we show here, right? Okay, so in this way, we can rewrite the formula for define the representation of the nodes inside the HRN, by differentiating the relationship among each other inside the HRN. In this way, we can learn the representation for the nodes inside this HRN effectively with multiple layers, and this representation can be further fed to some like a classification or some other task for learning the models. Okay, so this is the extension we can do to extend the GCM model to the HRN settings to consider the relationship types. We assign them with different weights instead.